Okay, so maybe we can start now. So, so let me uh, share my iPad. Yeah. Okay. So yeah. So this is your week 7 or almost the penultimate session for penultimate live session for your statistical mechanics course that you have registered in your NPTEL program. So yeah. So you have seen like the lectures which have been like uploaded for the last week or particularly week 7. So there were basically some tutorial sessions. So you have seen a lot of problems and instructor has uh, solved and discussed very nice problems over various topics that has been covered till that week. And so yeah, so on that footline only we will try to see. We are basically today we thought about discussing the problems of week 7 particularly, and see if there is any other issues we can also cover them. So yeah. So yeah, so these are your problems as follows in your week 7 assignment. So, and I hope you're trying to finish all other rest of the uh, questions of your assignments, including all the previous ones. So, if there's any issue, please try to clear them out as soon as possible, because week 8 will be your final week, and then probably one more live session we could have like this problem solving session, and where we can discuss for the final time, and probably that could happen on March of 17th. So yeah, and then you have to appear for your test. So that will basically complete your course. Yeah. So yeah, for now we can go through these following questions. Okay. So the first one right here is basically it has been said that just hang on a minute. हेलो हाँ पाया कुछ करने हेलो अभी मेरा वो टीए चल रहा था मैं कॉल करूँगा बाद में अच्छा ठीक yeah yeah I was talking about the problem number 1. So it says that like there are charges which are distributed on the corners of a tetrahedron. So like you can think of a uh, uh, tetrahedron maybe like this. So you have some kind of object of this shape. So 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 this is roughly a, shape of a tetrahedron having 4 corners. So Yeah. So now, let's say the question here given is like, uh, uh, what would be the entropy and the energy of your system if you distribute your charges on basically these four corners of your tetrahedron. So yeah. So suppose if you distribute no charge at all, so basically just say open corners, like then you have no. So let's say uh, let's say no charge, no charges are distributed. Then um, uh, then what would be your energy? So energy is like so. So before that, the energy of your system, basically what happens if you have charges, then this basically is simply Coulombic energy. So that is what the energy you will have when you have the charges. So uh, so uh, so energy, yeah, energy between a pair of charges. Uh, let's say uh, both of them have charge E, then it's basically U is E square over A, and so the distance here between uh, pair of a each pair of corners are, let's say, labeled by A, so they are uh, all the distances are here are A. So yeah, so when there are no charges basically, so you will have uh, zero energy and also entropy. So uh, so no charges means like even there are no entropy, like there are no different possible configurations possible or microstates. So even entropy is also zero. Then you can have so uh, then you can have number of charges n equals to 1. So basically, the question here is like, if you have different number of charges distributed on this different corners of the tetrahedron, then what would be your basically the uh, uh, I mean energies and entropy of the system. So yeah, so when there's no charges, so no energy, no entropy. So it seems like all the options that you see here, so they have this zero energy and zero entropy result. So in every way. So that is the common outcome that you have, but you need to single out one by considering more charges. So we can go with one number charge, two, three, and four. So if you have one number of charge, then again you have no. So it's basically this is your interaction energy. So when there's no such thing here self energy. So it's just basically the interaction energy between the charges. So when you have no number of charges one, still the energy U is zero, and entropy you can have you can like basically if you see the number of microstates, so number of microstates would be basically 4c1. It's basically 4. So you have non-zero entropy, but again, like there's no such option out here in the question given here, right? So uh, because zero energy, non-zero entropy, there's no not option. Maybe you can see uh, the other case if you have number of charges. Let's say that is 2 right now. So your energy is, of course, it will be e square uh, over 2, and your microstates. So if you see the number of microstates now which you can have. So let's say, so it's basically you have 4 different places, and you want to distribute uh, 2 charges. So you have 2 charges. So you want to distribute like uh, maybe so you want to distribute one over here and one over here. Then you can also distribute one over here or uh, one over here, or basically also one over here, or even one over here. So, uh, so if you calculate all these different um, possibilities, so I mean, so there are the number of microstates here is basically there are 4 different sides, and you can distribute 2 of them like in 2 combinations. Uh, So it would be basically 4C2. So you have 4 distinct sites and 2 charges you want to distribute. So it is basically 4C2. So and this 4C2 is basically 4 factorial and 2 factorial, 2 factorial. So that is basically C. So your entropy now will be basically S ln of microstate, that is S ln of 6. So now probably you can have an option which could match this result as well. So this outcome is E square over 2 for energy and ln6 for your entropy. So we are not considering. So let's say K is we are calculating entropy in units of Boltzmann constant K. So it's basically log 6 only. So log 6 and E square over 2. So so it's not E square over 2, it's basically E square over A. I'm wrong here, so that is E square over A. So the Coulombic energy. So E square over A and log 6. So almost all the options you have this outcome, but not the fourth one. So fourth one is not going to be one result here. So you have E square over A and log 6 in all these 3 cases. So yeah, you can check for the next case. So where um, your number of charges now is 3, then what would be your energy? So now your energy can be so you have 3 charges So your energy, interaction energy will be first. It would be due to this. So they are basically separated by a distance. Uh, these three of them are, I mean, all the three are distributed on the corners of uh, uh, so basically. So yeah. So let's say you have charges or one here and one here and one here. So yeah. So the energy. So the energy between this and this is E square over A, and also the energy between this and this is E square over A, and also the energy over this and this due to this and this is also E square over A. So all the three will take in pairs and their interaction energy will be calculated, and then you can just take the sum. So that is your total interaction energy. And it would be again same if you check if these three are distributed instead of these three corners, maybe it could have distributed in this and this and this, or it could be also this or this. So in either of these cases, your total interaction energy is going to remain same. That is the sum of individual pair of interaction energies. So that is basically uh, U is E square over A plus E square over A plus E square over A. So this is 3 E square over A. And again, so you have to distribute three charges in four places. So your total number of possibilities will be 4C3 this time. So this will be 4, and your entropy will be log of number of microstates. So that is ln4. So now your outcome would be 3 E square over A and log 4. So you will have 3 square over A and log 4. So you see that there is option number third, so which you have this case 3 square over A and log 4. So yeah, this is most likely going to be your answer for the first question, but you can check the last case as well. So because the last case you can see it's very evident that all the options that you see here, they have the same result, that is 6 square over A, but you can check why. So sorry, yeah. So the final case is the one when you have all four charges. Number of charges is n equals to 4. So then uh, yeah, so number then if you have uh, so if you have four charges this time, so the total energy would be like, like how many pairs which you can form here. Like if you are given like four charges, so uh, the number of pairs is also given, like uh, number of pairs with n equals to 4 is 4C2. So that is like six number of pairs you can form out of these four charges. Then uh, your total number of energy would be 6 times of e square over a, e square over a. So it would be 6 pairs, and that would be 6 e square over a. Then, so maybe you can check this. So suppose if you consider this is one pair, this is two pair, this is three pair, then these are three, so 3 square over 8. So this is 1, 2, and 3, and then you have this is 4, and this is 5, and this is 6. So there are total 6 possible pairs. Then your entropy. So there is only one way you can only distribute uh, uh, this charges. That is, so you basically microstates are basically one. So then your entropy is basically ln omega, that is 0. So we already guessed what would be our result. That could be, I mean, what would be our answer for this question. So that is, of course, going to be this. Then, yeah. So then we can move on to the next one here. So, so just a moment. Okay. Uh, so we can see the next one. So, yeah. Find the average of the square of the angular momentum in the harmonic trap problem. So, so we have to look onto this problem, harmonic trap. So which is already there in your lecture. So you can, so probably you have seen it, or if not, then like what's basically harmonic trap is a system that is given by this. So your Hamiltonian of your system would be your kinetic term, that the usual kinetic term, that is p square over 2n, plus you have something like a uh, restoring type force. I mean, it's basically the I mean, like a spring system, k by 2 over r square. Uh, yeah, and in and if it is a like a rotating gas molecule, so it's like something. Um, so so it is like this. So this is your, like system. So of some mass n. This is your block of the molecule, and it is under this spring type force, and it also can rotate. So yeah, so it can rotate with some angular velocity. So yeah, so it's then its probability is basically then proportional to uh, something exponential minus beta uh, h, and also omega dot L. So omega is the angular velocity and the L is the angular momentum of that molecule. So and in this case, if it is given to be z direction, and we are looking only for single particle. So let's consider only single particle. So uh, yeah, so if there be many particles, you would have been summing over all i's. So we are only looking for a single ith particle. So and yeah, it is given for, if it is given for z direction, then it would be simply h minus omega uh, lz. So let's say omega is or something omega not lz. Let's and so we need to calculate the uh, square average of the square of the angular momentum. So your angular momentum is Lz. So it's square, you have to take the square and then the average. So Lz square average. So and this Lz is basically xpy minus ypx, and then your Lz square is basically x squared py square plus y square px square minus 2y of xy px py. Yeah, so that will be your Lz square. Uh, Now, like what you can do here, so you can directly do the phase integral type calculation where you can take the average of the quantity. So taking taking it with the phase space probability. So you can see the like in the lecture. So in the same tutorial video, so which is there in your week 7. So in tutorial 2, so you would have seen the instructor has calculated some quantities like some x square average, where it's something given as the entire phase space, like I mean it would be something like dx, dy, dz, and then also it is summed over momentum, like dpx, dpy, dpz. Then you would have something like exponential of uh, so you are taking x square average, so that is x square, then exponential of minus beta h minus omega dot l. So yeah, and then uh, for normalization we'll have this again. So dpx, dpy, dpz, then so yeah, so you can take the average because I mean this is how it has been calculated in the lecture. You can check the video again once more and see uh, like how it can be calculated. But then likewise you have to calculate one more time what would be y square, which would be just, you can follow from the result of x square average, and like and then z square average also you have. I mean I think this would be also given or calculated in that video, you can check. And then in the same way you have to calculate px square, py square, because Uh, uh, yeah, the, so you have to take LZ square average. So you have to take LZ square average. That means you need to take uh, so you need to take the uh, uh, so to calculate LZ square average, you basically need to calculate x square py square average, that is x square average py square average, because you can separate them out because x and y, they are independent coordinates, and then same way you have to calculate xy px py, and it will be something like xpy average and ypx average. So all these average quantities you have to calculate, and then you can get exactly what would be LZ square average in the harmonic graph system. But instead of going all this way, you can also check this result using the following intuition. So what you can do, your Hamiltonian, which is given, or the total energy of the system, which is given, so that is basically H minus omega Lz. Let's say omega naught is the angular velocity for the z component, and Lz is angular momentum. Then H is basically, as we have seen, is p square over 2m. So p square is basically here. P square is px square plus py square plus pz square, and again your r square is x square plus y square plus z square. So that means so you have basically your results. Uh, just wait a minute. uh, just yeah. Sorry. Okay, so your what would be your momentum? So I mean your total energy would be this over 2m. Then you have plus k over 2 x square plus y square plus z square. Then minus omega uh, xpvy. So it is minus ypx. Then Then suppose if I like what I can do, I can write something like if I group this expression into this way, px square over 2m plus uh, omega y px, omega y and px. So this is basically 1 over 2m px over m omega y square minus m omega square y square over 2. Uh, um, okay, that is fine. And similarly, I can also write, uh, I can also write this following: py square over 2m omega uh, xpy, which is 1 over 2m py minus or plus uh, this would be minus m omega x, then it would be minus m omega square uh, x square over 2. Okay, so if I let's say that this is restricted on xy plane because uh, omega points in the z direction. So is if your omega is in z direction, so if your omega is in omega z direction, then so this harmonic trap system is on your xy. So that means your total energy, which we have been writing, will basically become this px square over 2m plus omega y px, uh, or not this, or the expression which we unfolded here. So that is px plus m omega y over square over 2m. So that is like effective momentum along x, and similarly you have some effective momentum along y, that is this, and this is like some effective spring constant and along radial distance of on the plane. So you have, so mm, this like p effective, or yeah, p effective x component, and this is p effective y component, or better, let's not call that way, but what we found here, we have some effective spring constant, that is k effective is k minus m omega square. So sort of like you can think of like your harmonic oscillator system that you are having here with some effective definitions, with new redefined definitions of your spin constant and momentum. So so now what happens? So in order to get the result, I mean to calculate this without any solving any Gaussian integral, without following the approach of calculating each x square average and py square average, what you can see here, what you can check. So omega square is basically you see if for omega square value k over k by m. So this effective uh, spring constant that you get here, so it can for a definite value of k, it can become zero. So that means here this means I mean k effective can become zero. So if k effective becomes zero, so then basically in your system what you have, so you have only kinetic terms, and there are and the potential is and the potential will go to zero if k effective is zero. So your h minus omega not Lg is basically uh, some px plus m omega y square over 2n plus py minus 1 omega x square over 2n. So it's basically like free particle system. And if you take this means if you take uh, for a for a free particle type system, and if you take angular momentum square average, so it can go to some large value. So it can be very large or infinite. So from the options that you will see, so uh, omega square when it becomes k over m, then you see your Lz square average will diverge. So and you see that it happens only for this option and this option. So so from here you can say that definitely option B and C, or the second and third, cannot be your average value of this angular square of angular momentum. So it has to be either one or two, and then you can check one more limiting case, or one more limit for you can completely single out your option. So in the limit in the limit omega equals to 0, uh, or basically omega not equals to 0, your h is basically simply this, or uh, your h minus omega naught Lj is basically h, that is just simply px square plus py square over 2n plus k by 2 x square plus y square. So that is purely like a harmonic oscillator type system. And uh, and this, like if you have uh, like if you want to know what is the uh, average value of if your energy now becomes completely this, so your exponential minus beta h minus omega naught Lz becomes this exponential minus beta h. So in this case, you can use the idea of equipartition. So from equipartition law, so your every square term will give you some half cavity contribution. So like you have half k x square, and if you take average, so this will give you uh, So this will give you, let's say, some energy. So I'm taking in terms of kbt. So kb I'm taking it to be 1 Boltzmann constant. Then this means your x square average is this will be half t. So from I can say right from equipartition. So now this is basically x square average is t over your spring constant, and similarly you can have ex square over 2m as half t. That will again give you something. Ex square average is m times t, and for any other non-quadratic type terms like your xpy average or ypx type average will have 0. So from there you can easily guess what would be your LZ square average, uh, which we initially said it would be x square py square plus y square px square, then minus twice of xy px py. So that will go to 0 because of this. So you will only have x square py square average plus y square px square average. Now this is something will become uh, t over k, then mt plus t over k mt. So this is something will basically become 2 mt square over k, or basically this is lz square average is 2t square over k over n. So if you check the option again, yeah, for omega equals to 0. So remember we all did for omega not equals to 0. So this becomes more or less like a system of a harmonic oscillator type, and from there we found out what would be the actual value of Hz square average. So that would be something 2t square over k over n. And if you see that omega equals to 0, only this fourth option like is going to give you 2t square over k over n, 2t square over m over k basically. Uh, yeah, well, it is. Yeah, this is what you will get. So your uh, so your actual answer will be, so this tells your actual answer will be 2t square k by n, then you have k by n 3, I think it was omega square minus k by n. Yeah, so finally this is going to be your answer. So yeah, that is what you will have. So if you have any doubt or something, please ask. Okay, we can look for the next one. So it's a bit of a more of a mathematics exercise. So uh, what is given right here, you have this Euler-Maclaurin relation, and from there you have this. I mean, this remainder value is approximated to be this the last term, and if the function given would be this exponential of minus alpha modulus of x, uh, then uh, what would be your basically your R value. So you have to determine what would be the R value here. So okay, so here what you need to do here is like the Euler-Maclaurin formula is given to be this, and the R value is said to be this, like it is some minus 1 over 1 12 minus 1 over 12 of this f I mean this derivative of the function f of x at x equals to 0. So f of x is given to be this, and then in that case determine the value of alpha. Basically you have to need to know what is alpha, for which the value of alpha corresponds to the value of r, that is 1% of this integral, or this expression. So basically this expression is this right here. Okay, so your f of x is given to be exponential of minus alpha mod of x. Then uh, so for x greater than equals to 0, you have f of x equals to uh, exponential minus alpha x. So then if you calculate, if you use that in Maclaurin relation, so from Euler-Maclaurin formula, the first term, you have this f of x dx integral. You have to evaluate this integral for the first term of the Euler-Maclaurin uh, approximate relation. So where x goes from 0 to infinite, so it's all positive x. Then so that is basically 0 to infinite exponential minus alpha x dx, and this is a very familiar uh, gamma integral. So which it will give you, um, or you can basically uh, do a simple integration, and this will give you this minus 1 over alpha exponential minus alpha x. So basically take the integration of exponential, so that is exponential minus alpha x, so minus alpha from 0 to infinite. So this is uh, So exponential of minus infinite is 0, and then so you have exponential of 0 is 1, so 1 over alpha. So it's basically 1 over alpha you will get. And uh, so this is your first term, and then you need to know what is second term. So the second term is basically uh, half of f of 0. So half of f of 0, so that is uh, half of uh, f of 0, that f of x is basically exponential minus alpha, so alpha of 0 is 0, I mean f of 0 is exponential of 0, that is so 1 over 2. And uh, and for the remainder you need to calculate the derivative for the third term, that is your remainder, so which is given to be r equals to minus r is approximately minus 1/12 of prime 0 of f prime 0. So so if you take what is f prime x, so f prime x is basically minus alpha exponential minus alpha x, and so f prime 0 is basically minus alpha. So your r basically becomes alpha over 12. Now what is here further given, your r is also said to be also given r is 1% of, so r is basically 1% of this 0 to infinite f of x dx plus half of f of 0. So r is also this, and if you see, this is something which we have calculated. So integral of f of x dx is 1 over alpha plus uh, uh, half of f of 0 is half, and this basically becomes r as we just evaluated, that is approximately alpha over 12. So this is approximated alpha over 12 and 0.01, 1 over alpha plus half, and yeah, so it will give you some quadratic type uh, relation. So from there you can calculate what will be alpha exactly. So here, if you solve this, you can get the alpha, which is uh, the basically the second option. So 0.37707. Yeah, you will have this result. Okay, if there's any issue or any problem, please uh, just wait for a moment. Yeah, so yeah, we can look for the next one. So next, what you need to do here, you need to get this legendary transformation. So this legendary transformation of entropy with respect to this thermodynamic variables, internal energy, uh, which you can get it by trading the temperature variable, and by trading pressure or temperature you can have volume, and then likewise number of particles for chemical potential. So basically, you need to first find out the Legendre transformation of the entropy. So, uh, so as you can see clearly here, the entropy is given something of the uh, form of some internal energy, volume, uh, and the number of uh, particles. So, and also from thermodynamic relation, which you know from dynamic relation or the first law of thermodynamics, you know, the entropy is something given as TdS equals to du plus PdV, then minus of mu dN. So mu is your chemical potential. And now, so if you see the derivatives of entropy with respect to this UV and variables, then you have this with respect to internal energy will give you 1 over temperature, and with respect to volume it will give you pressure over temperature, and with respect to number of particles it will give you minus yeah, negative of mu over t. So yeah, that is why if you see the internal energy as written in the question, so it is traded for temperature, and uh, volume for pressure and temperature, and uh, number of particles is for chemical potential and temperature. So these are like conjugate variables for you. The internal energy, the conjugate variables is 1 by 2. So u and 1 over t are conjugate variables. So likewise, v and v over t and n and minus v over t. So now what is Legendre transformation here? So Legendre transformation, if you remember, like one of the very well-known Legendre transformation that you have seen, or at least in classical dynamics, that is going from Hamiltonian formulation to Lagrangian, or going from Lagrangian to Hamiltonian. So if you do that, like when you go from Lagrangian Q and Q dot to, if you when you go from Hamiltonian Q and P, so you do this Legendre transformation, which is given as Hamiltonian of Q and P, Qi and Pi, let's say. So summation over I. So Pi and Qi minus L of Q and Qi and Q dot N. And there'll be Q dot here. And this Pi is basically given as del L over del Qi dot. So similarly, similar legendary transformation you can also write here. So if you make uh, L as your, I mean L the Lagrangian that you know, you can, so you are now, you can think of this as your entropy function, which is function of U, V and N, and then so this is your conjugate variable for basically canonical coordinate corresponding to your canonical coordinate in your Lagrangian formulation. So that is, so Uh, yeah. So what happens if your Lagrangian is something, let's say, some function of x, y, and z, and also x dot y dot z dot, then you have then the summation will run for all x, y, z. So so then your Hamiltonian is something given as x. Uh, yeah, if it is given as x dot plus y y dot plus z z dot, then minus of L. So same way you also have now, and this is further written as x. Uh, I mean, uh, and further what happens? You can write x dot in terms of some. I mean, using uh, so you have something px as del l over del x dot. So from there, you will get a relation between px and some x dot, uh, let's say some function of x dot, and from there you can substitute your Hamiltonian in terms of px. So it would be now something x and some function of, let's say, f tilde px and plus y from f tilde py, and likewise you have then minus l. So same way, the idea here is also going to apply. So uh, so let's say if you when you do legendary transformation of L, you get H. So now when you get H, and when you do legendary transformation of S, let's say you get S tilde. So now your legendary transformation S tilde is given a this is now mm, summation of variables. So the summation will be over u, v, and n. So let's say uh, pi and qi minus uh, let's write pi and xi minus f of yeah, minus s of xi. So your xi's are basically u, v, and n. So your s tilde is now given as let's say p1 x1 plus p2 x2 plus p3 x3 minus s is your entropy, and this is p1 u, let's say x1 is your u, p2 x2 is v plus p3 and minus s, and p1 p2 p3 are basically your I mean your pi is basically given as del s by uh, del xi. So so if your xi is u, then your pi will be del s over del u plus del s over del b b plus del s over del n minus s, and this as we have evaluated here. So del s over del u is 1 over t, del s over del v is 1 over, so p over t, and del s over del n is minus mu over t. So yeah, so you have right. So your um, S tilde becomes uh, so your S tilde will become u 1 over t u plus uh, then p over t u, which is v, then minus mu over t and minus s. So yeah, so now you can say, so initially which you had entropy, it's legendary transformation basically gives you something of this s uh, uh, so let's say you are writing it is giving me something of s tilde form. So legendary transformation is basically giving you s minus u over t plus mu over t n minus p over t volume. So this is what your legendary transformation gives you. So you went from so you had S U V N. So upon legendary transformation, you went to 1 over T, P over T, and minus 1 over T. Okay. So so you will have this option to be correct. So if you see the option third, it will not match the sign. So if you are considering a legendary transformation, let's say S from minus S tilde, then the option 4 will match. And if you are trying to see S2 S tilde, positive S tilde, then none of the options will match. This S tilde, minus S tilde. Yeah, if you have any problem, you can speak. Yeah. Uh, so next, what you have here, this following question. So it is given that the water in a glass, which is boiling, uh, and the water molecules are of mass m each, and they are boiling at a temperature which is kept constant at temperature Tb. It is measured in some energy units, and then there are n naught molecules filled in it, comprising of volume, some uh, this cross section area A, and times h naught at, at the initial time, that is t equals to 0. So that is something thought of as a ideal system of particles obeying Maxwell's Boltzmann distribution. So then the molecule evaporates. It exits the glass if the z component of its momentum exceeds a certain critical value, pz greater than pre-critical. So then the molecule will escape from the glass when its momentum along z, or its z component of momentum becomes greater than a certain critical value of the momentum, that is p critical. Then that molecule is escaped or is basically evaporated. So that is what the problem is said, and uh, then so you need to now calculate what would be the number of uh, uh, just a moment. Yeah. So that is what the problem is given. Uh, so then the first question here is number of water molecules remaining in the glass after some time uh, t greater than 0. So first, as we know that the water will only escape, or the water is on. I mean, the water molecule only escapes, or the water molecule evaporates when its z component of momentum exceeds the critical value, that is p critical. So, so in that case, it is also said that uh, the this distribution of water molecules in the glass can be modeled as an ideal system of particles following Maxwell-Boltzmann distribution. So for that we can write down a distribution of molecules for its momentum, for its z component of momentum, can be written down as f of z obeying this Maxwell-Boltzmann relation, which is basically a Gaussian type of distribution. So it can be written down as 2 pi m dv exponential uh, minus ez square over 2m dv. And so now to calculate number of articles uh, crossing uh, crossing uh, top surface per unit time per unit time per unit area, or basically rate of uh, crossing of water molecule is given as 0 to not 0, so it only crosses when uh, let's say 0 to infinite Vz f of Pz d dpz. So this is basically the uh, rate of water molecules that is traveling. So to calculate the rate is basically given by its velocity. Uh, so here just note rate of water molecules crossing is basically the, yeah, it's basically related with its velocity with which it is moving. Uh, right. And so if you evaluate this integral, so that is first there are, if you know, there is a critical momentum beyond which only water can escape. So let's say this Pz can be written as Pz over m. So 1 over m Pz. So it is basically 1 over m is equal to infinite Pz f of Pz Pz. And so if you see 1 over m 0 to P critical Pz f of Pz dpz uh, plus P critical to infinite Pz f of Pz dpz. So so this is like the total rate of crossing. So this is total rate of crossing. So uh, this is it's, uh, so this is the total rate of crossing. But to now for the to know the rate of crossing from the top surface, you need basically the second integral, that is 1 over m P critical to infinite, because only then the moment the water molecules having Pz greater than P critical can only escape. So that is why the only second integral will contribute. So yeah, now yeah, if you do this integral, so you can use the distribution function which we initially uh, taken it to be Maxwell-Boltzmann, which was set in the problem. So 2 pi m dv, and you have to integrate out this momentum ev and exponential pv square over 2m dv dv. Yeah, again, now you can evaluate this gamma integral. So this integral is something of this type. So you can see x of exponential minus x square over b from a to infinite. Then this integral is something given as b over 2 exponential minus a square over. So using that, you can write down the expression of this integral, and finally if you solve this, so you will get it to something dv over 2 pi n, so which is under this square root and exponential minus p critical square over. So again, I have taken this to get this won't be 0, this is p critical. So p critical is over 2m dv. Yeah, so let's call this something as n tilde. And so now number of molecule living or rate of number of rate of molecule leaving the top surface is dn over dt. Uh, so or otherwise this is, let's say, escape rate is given as the total cross section area, then times the uh, number of particles leaving the surface, that top surface, that is n tilde, uh, uh, n tilde times the uh, number density. So number density is n, that is a n tilde n by v. So since these are leaving the surface, so this will be negative. So yeah, you have dn over dt, that is minus a n tilde n by v, and further v is given as a times h naught. So this will become minus n tilde over h naught, and yeah. So basically dn dt is minus n tilde over h naught, and your sorry, n over h naught, and your n tilde is the one which we just found out right here. So that is square root of dv over 2 pi n exponential minus p critical square over 2n dv. Yeah, and now it's just simple to see that. I mean, it's just if you integrate out the number of particles. So for t greater than zero, or uh, yeah, for t greater than zero, so your n of t. Uh, uh, so for your n of t, it's basically minus n over n over h naught dp over 2 pi n e square critical over 2m dv times t. So so your first problem was number of water molecules remaining in the glass. So now number of water molecules remaining in the glass, remaining, that is n minus n of t, that will be n minus n over h naught dv over 2 pi n exponential uh, yeah, minus p critical or 2m dv times t. So that is, so n time, let's say, is your number of particles remaining, that is n times 1 minus t over h naught dv exponential naught minus p critical over 2m dv. So yeah, so this is your remaining number of water molecules uh, in the boiling glass. So it should be this. Yeah. Then yeah. Then the next which you need to calculate here is uh, the volume of water remaining after time t. So to calculate the volume of water remaining, we can use the number of molecules that was remaining. that information which we just found out. So we have that expression. So one thing as we could see here, uh, so as we the density of water that which we are seeing, so that is like taken to be constant. So density is constant. I mean, so density of water is constant. So that means your n over v is constant. Your n, and this also means that n uh, n by v is also n of t, and v of t is also constant. That means uh, we can calculate what is v of t. Uh, so this is n of t, v of t is basically, so the escape number of molecules. So let me be clear. So this will be n prime of t and v prime of t. So n of t is escape number of molecules, and n prime of t is remaining number of molecules. So so this will be equal to this, and with n of t, and this is n prime of t. Okay. Yeah. So remaining number of volume. So remaining volume is v prime of t is given as uh, v over n, n prime of t, and so v prime of t is v over n, and n prime t. So n prime t, which we got it right here. So that is n times 1 minus t over h naught t over 2 pi n exponential minus p critical square over 2 mp. So from there you get p prime t is v 1 minus t over h naught t 2 pi m exponential minus p square critical over 2 mt. Yeah, so that will be, so your third option would be the correct one. So yeah, then we have, I think, one more final question related to this. So yeah, so the finally it has asked like what is the total time taken to completely evaporate the water. So to completely empty the glass. So when all the water is fully evaporate or the glass is emptied, then you have remaining volume is zero. So this is remaining volume is zero. So yeah, so when your remaining volume is zero, so you can use the remaining volume which we got right here. So that is uh, yeah. Uh, so your remaining volume is V1 minus T over H naught T over 2 pi then exponential of minus P critical square of 2 pi m minus 2 mt. So this goes to 0, and this will only goes to 0 if you have uh, T over H naught over dV over 2 pi m exponential minus P critical square over 2 mtd is 1. So this is basically time is given as H naught times 2 pi m over td, and this P square critical. So you can see now it scales as exponential of something P square, so exponential of positive something. Uh, so it will take a very last time. Yeah, yeah. So you get it to be this. So then the correct option would be the last option. Yeah. So this is your final option. Yeah, and so more or less like we have just covered all the problems of your assignment 7. So you can see, check the solutions and see if there is an issue. Yeah, so and this is what even in the tutorial you would have seen some related problems of the week 7 which was uploaded in your like in your NPTEL course. So I hope you are going through them regularly and like I mean, learning the lectures, learning different topics of the week, and because without going into the topic, particularly its basics and its understanding, then you won't be able to go near to the problems which are given in the assignments. Which so yeah, you need at least some idea before jumping into the problems of of the corresponding week's assignment. And yeah, so even we have seen some of the problems which right here today as well, like they are the topics or the problems or relevant problems, something which was also solved during the week's lecture sessions. So yeah, so hope you are like finding the lecture videos, you were able to access them. Like, there's no issue. Like they were at one point there was some issue like where I mean there was some delay in uploading the lectures of week 6 I guess, but I think week 7 week 8 is already on time and or maybe before time. So um, so hope you were going through them and like yeah. So couple more sessions we would have, like I mean one would be the last week 8 session where we would see try to solve this kind of problems or related problems of the week 8, and or if there's any additional new topic of the week we can also look into it. And then um, uh, yeah, then following it we can we'll have one more last session, so that will be a concluding session where we'll recap some of the important topics or problems, or we'll see some review of some interesting problems or something very crucial problems in like that could be relevant for your test. And yeah, we'll try to discuss them thoroughly as possible. And yeah, so more or less like we are done for today. So if there's any problem or any uh, issue in understanding anything of it which we covered, so uh, please let us know. Okay, if there's no other question, maybe we can stop here. We can meet again next week. Uh, yeah, so see you again. So yeah, until then, goodbye.